Okay, so this is a joint work with Pavel Dvořák. Actually, Pavel was supposed to give the talk, but for some reasons he couldn't come. Okay, so supercritical trade-offs. Everybody knows about this Cook's program for showing NP different from co-NP, where we would like to consider stronger and stronger propositional proof systems and try to show super polynomial lower bounds for them. So our work is located broadly in this context. And here's what we know. So these three proof systems would be relevant for us. At the bottom is resolution, which is a very basic proof system, which is P simulatable by AC0 Frege. AC0 here means constant depth. And we have lower bounds up to here. And then, this is contained in AC0 constant depth Frege with the mod 2 primitive added. And of course, if you think, we know circuit lower bounds for AC0 mod 2 for long, but in the world of proof complexity and propositional proofs, this is a major open problem. Not much progress has happened. And then in 2014, Itzik and Sokolov introduced this interesting model, which is a variant of resolution by adding the mod 2 counting primitive to it, which they called reslin, and we will denote by this. So it sits somewhere between resolution and AC0 mod 2 Frege. And the idea was that this is it seems like it's just a perturbation of resolution. So if we want to prove eventually lower bounds against AC0 mod 2 Frege, so it would be good to understand this system. Unfortunately, for general reslin, I would often call this reslin. For general reslin, still there are no lower bounds, although there has been some very interesting progress that has recently happened, but we still don't know for unconstrained reslin super polynomial lower bounds. So our work in trying to prove supercritical trade-offs here is trying to understand this system much better. Okay. So the two fundamental complexity measures that is going to be relevant for us because it was relevant for resolution is this width. The width in resolution is, so a resolution proof is a sequence of clauses, and you look at the largest width that appears in any clause, where the width of a clause is just the number of literals that appears there. Okay, so the width is a very basic complexity measure. And then you have size, which is the number of clauses. This is much easier to deal with generally. Yeah, this is much easier to deal with. This is usually more difficult. But then Ben-Sasson and Wigderson in 2001 proved a very nice connection between the two, which says that if you prove lower bounds on width, that's sufficient to prove lower bounds on size. Okay. In particular, they showed this relationship. Now, the first one is for tree-like proofs, something that we will start talking about more. And the second one is for more general DAG-like proofs. Okay. So in words, if you don't have to understand, there's a log here that's interesting to remember. So if your size is like 2 to the n, then your width would be n. Okay. And the general idea is here, as they summarize it, is that short proofs are narrow. So if your proof is short, then you can convert it into a narrow proof. But the important point here is, well, the proof that you start with, which was short, that need not be narrow. But there is a different proof that might become narrow. Okay. And the question that we want to ask here is, well, how long do narrow proofs have to be? So if you start with a narrow proof, it's sort of a question from the other side. How long does it have to be? Okay. So in general, there's a very trivial upper bound that you can get because you just list down you do the brute force thing. You look, if your width is W, you look at all possible clauses of width W. Okay. And there are these many clauses. So if you have if you're going to use DAG like proof, you can reuse clauses that you have derived. So the size would be trivially upper bounded by this. Yeah, this is a trivial upper bound. But what happens if you want to make your proof a tree-like? Yeah, then what can we say about this upper bound on size, given that the width is small? And this is where Razborov's result comes in 2016, which is a very strong trade-off, strong and surprising trade-off between width and size of tree-like proofs for resolution, where he showed that take any function k of n, so it's a growing function, and take any epsilon is a constant, then there exists a sequence of contradictions tau n, yeah, parameterized with k, such that they all can be refuted in width k. So if k is a constant, they're really small width refutations. But for any tree-like proof, which tries to refute it in slightly better than trivial width. So the trivial width is n. Yeah. So if you try to do slightly better than the trivial width, then the proof size shoots up like this. So it becomes, this is an exponential of n to the omega k, right? So 2 points to note: if k is a constant, then this, although this has as I said, very narrow proofs, every narrow proof, a tree-like proof, has to be super exponential. So imagine k is like a large constant 10, so it's exponential in n to the 10, which is super exponential. And if you make k to be a small growing function of n, like n to the 1/3, yeah, then even if your width is slightly off n to the 2/3, then the proof size will become doubly exponential. Okay, so this is a really very strong trade-off. And Razborov nicely summarized it in his paper by this picture, where this is, as he called, the critical line. So you are plotting size versus width of proofs. This is the critical line because any proof naively, any proof will have size length at most 2 to the n, because you can just make a tree-like proof. Okay, and what he shows is if you look at these contradictions and try to find the size of the proof which is with minimum width, then it shoots up way beyond the critical line, and the whole trade-off stays above this critical line. So this is a remarkable thing, because usually trade-offs would fall off the critical line. For example, if in communication complexity, when you look at rounds versus communication trade-off, you obtain trade-off results which go this way. Yeah, here the trade-off is going way above the critical line. And he called it a rare phenomena in all of complexity theory, and gave a call for discovering more such trade-offs. And in response to that, there have been several works. I'm anyway very new to proof complexity, so I may not be knowing extensively about this literature, but let me just cite some of them. The first one is due to Berkholz and Nordstrom, who did a similar thing, but now with respect to space and width and resolution. So the proof system was still resolution. And then there was a paper by Fleming, Tony Pitassi, and Robert Robert, who showed the same thing, but extended the reach of Razborov's techniques. So first of all, they observed that this can be generalized to DAG-like resolution with resolution K, cutting planes. And very recently, there's been some very exciting progress by 2 groups of independent researchers, Derezen, Fleming, Janet, Nordstrom, Peng, and Goose, Mest, Rees, and Sokolov in 2025, that shows similar phenomena also appears for monotone circuits. Yeah, depth versus size, answering a question that had been open for long. So our work is in this vein, where we try to now see if supercritical trade-offs can be proved for res-lin, yeah, resolution with the parity clause added. Yeah. So this is the question we had in mind when we were thinking about this. Well, of course, we cannot hope to prove it for general DAG-like res-lin because there are no strong lower bounds. Okay. So the question is, can you prove it for tree-like? Because for tree-like, in the original paper of Itzik and Sokolov, they already proved several lower bounds. And moreover, we have lifting theorems for tree-like res-lin now for a while. So let's look at the two lifting theorems that sort of we know for a tree like Breslin. So the first one says that if we take a contradiction, lift it with an appropriate obfuscating gadget, and if we find that it has a refutation in Breslin of size S and width W, then one can extract a resolution refutation, tree-like resolution refutation for the base contradiction tau n of depth order log S. So here we had size S, and now we go to depth order log S in a weaker system. And more recently this year, Alexeev and Itzikson proved the following. You consider any Breslin refutation of a lifted formula which has, let's say, rank W. So in a Breslin proof, every node corresponds to an affine space, unlike a cube in the case of resolution. And the rank of that affine space is the natural notion of width. Okay, so this is why the width gets replaced by rank. So if you look at refutation of rank W, then they can extract a refutation for the base formula also of width order W. Yeah. Now, can we use these two? There are two lifting theorems, slightly different in flavor, but they both suffer from one common weakness. The first one, although I stated that the width of the Breslin proof was W, paid no attention to the width. So it may not be width preserving. When you extract a base proof, the width of the proof might blow up. Okay, especially imagine this log S. S was like an exponential function or doubly exponential, and then width could have been much smaller. So you get no meaningful bound on width when you extract the proof in the lower system. Sorry. And in the other case, there is no mention of size. Okay, so they're able to preserve the width, but there is no mention of size. So if you want to apply this lifting formula to directly Rasborov's formulas, you actually don't get anything. So what we do here, which is the main technical contribution, which is a lifting theorem, which is sort of a common generalization of those two theorems. Yeah. Now you start with, again, a lifted formula. Now G is a slightly different gadget. We will come to this, the nature of the gadget, later. So look at a lifted contradiction. If it has a tree-like Breslin refutation of size S and width W, then you can extract a tree-like resolution refutation whose width is preserved, it's at most W, and the depth is order log S. So you can shrink the depth, keeping the width intact. Okay, so that's the common generalization. Okay, and it doesn't take too much to realize that once you have such a lifting theorem, if you add Rasborov's result, you get supercritical trade-offs for, I should mention here, tree-like Breslin. Okay. So the main thing that powers this whole thing is the lifting theorem. So from now on, I'll just focus on the lifting theorem. So let me remind you what resolution and Breslin are for a second. So in resolution, it's a very basic system. If you have, the basic rule is if you have two clauses like this, A or X, B or not X, then you resolve on X to get A or B. Okay, and the idea is you start from the axiom clauses and you derive the empty clause, thereby refuting the satisfiability of your given contradiction. And you also have the weakening rule, which is when you can introduce a new variable. In Breslin, it's analogous to this. You start with, instead of clauses being an OR over literals, now you have OR over linear equations. Okay, so these are called linear clauses over F2. And this is the resolution rule, which is a very natural correspondence. Instead of having an X here, you have a linear form. And so two sets of clauses appear in one in which the linear form gets the value 1, the other is 0. You resolve on that and you get A or B, which is a very natural thing. Yeah? And then you can do the weakening as well. Yeah? But the important thing to remember here is that in resolution, you work with a fixed standard basis. Yeah? So the resolution has much limited power. Whereas here, you can reinterpret your clause by changing basis. So there were two clauses which looked very different, but then you realize that there's a common basis in which you could resolve. Yeah, which just doesn't exist in the case of resolution. And this is what makes, understanding resolution with parities much more difficult, because you can arbitrarily change basis. There's no one universal basis. Okay, so having said that, the way I would like to view these things now is the standard reformulation of the thing, where I go to this falsified clause search problem. Okay, so given, let's define this problem. Given a contradiction, I know that this is unsatisfiable. So if I give any input x, so this is a total search problem, I have to output a falsified clause. There may be many, but just pick your favorite one and output that. So this is the falsified clause search problem, and it's well known that a tree-like resolution proof of a contradiction gives you an algorithm, a decision tree for finding the falsified clause. Yeah. And similarly, in the same vein, if I give you a Reslin proof of a contradiction like this, yeah, you get a parity decision tree. Yeah, for just the parity decision tree that the previous talk was mentioning. You extract a parity decision tree. It's in one-to-one correspondence for solving the falsified clause search problem. Now, there's a twist between my talk and the previous talk. In the previous talk, the talk was about computing Boolean functions, so decision trees would never forget. They would query, and at any point at a particular node, the codimension of the cube that you are in is the number of variables along the path that you queried. Because we are dealing here with proofs, and proofs with a constraint on width, our decision trees would be forgetting. Yeah? This is a notion that's not typically used when we talk about decision trees computing Boolean functions. Okay, but for this falsified clause search problem, this is an important thing. So the trees would have this property of forgetting, so they are forgetful. Some of the nodes would forget, and similarly here we will have forgetting PDTs. Okay. And let's carefully look about these things. So, my claim is, and this I won't have time to get into, but this is very simple, that you can classify your nodes into two types in a decision tree, which has been extracted out of a proof. One kind of nodes are called query nodes, where it's like the usual node. You query a particular literal variable, sorry, xv. And if it's 0, you go on this side. If it's 1, you go on the other side. Now, at every point, I'll assume that you have a set of partial assignment. You've been given the input x, but you're only remembering a certain parts of x, which I'm maintaining as a partial assignment. So when you query at the node v, then your partial assignment, when you descend into u, your partial assignment extends in the following way. Whatever you had over here, you add to it xv equals 0, and similarly the other way. And the same thing happens on the other side. Yeah, except now you have affine spaces, and your new affine space is just its codimension goes up by 1 by saying LV is equal to 0 or LV is equal to 1, whichever the case is. So this is the usual query node, which you also have in your parity decision tree, the usual parity decision tree. But as I promised, there's going to be forgetful nodes, and these are the problematic nodes. Yeah, these are more complicated nodes because, well, over here it's sort of simple, because when you forget, you are in the standard basis, so you forget a particular variable which you were remembering. Yeah, so imagine you were over here you forget a variable xv, whatever its value was, it gets freed now. Yeah, so you have one less fixed variable. Sorry. Over here, it's a little bit more subtle, because you just descend into an affine space which is containing you. Yeah, so there's no clear notion of what you forgot. Yeah, you can always recast it as forgetting, but you have to change the basis perhaps. Yeah. So all you can say is, in this linear algebraic language, of the codimension of the space that you descended in decreased. So the dimension of the space increased. Okay. So these are the two nodes, and now I'm going to only talk about decision trees in the rest of my talk. Okay, I mean, we have abstracted out what a proof is, and we are only going to talk about forgetting decision trees and forgetting parity decision trees. So the lifting theorem would be, given a forgetting parity decision tree, how do I extract a forgetting decision tree? Okay, so and the idea of doing this is as exists in the communication complexity literature. You know, okay, my task when I'm trying to prove a lifting theorem is to construct my decision tree algorithm, given in the background that I have a parity decision tree algorithm. 5 minutes. So in this algorithm, I'm going to always remember, so in this particular algorithm, I'm simulating this, and everywhere at every node over as I descend down this path of a parity decision tree, I'm going to remember the set of partial assignments that I sort of so far remember. I remember in my algorithm. Yeah. So X, the input, is contained in this cube that I'm currently in, and this will be my number of fixed variables, which is equal to the codimension. And over here on the other side, I have this affine space. Okay, so what's our goal? The main goal in this kind of simulation thing is that, you know, I want to maintain this following invariant, which is going to be the very crucial thing, that I don't know, because I have an algorithm which is not trying to probe too much into the input X will always have a representative in the affine space that I have descended in. And by representative, I mean, if you apply this gadget, yeah, on this input Y in the lifted space, I should get back X. Yeah, if I can maintain this invariant, then wherever I am, I can mimic the answer that is given by the decision tree, the parity decision tree, to get back the right answer that I need. And the other thing, because I want to maintain the width, the number of things that I'm going to remember should be at most the codimension of AV. So if I can maintain the second invariant, then I know that I'm never going to exceed the width budget. And finally, I want to do all this in such a way that the maximum number of simulation steps that I'm going to do in my algorithm is never going to be more than log roughly the size of the decision tree. Okay, and stifling gadgets will help us in this for the following reason. So, when do I call a gadget stifling? This was a notion that was introduced earlier in our work. So imagine you have a gadget G, which is acting on B bits, and you give me an arbitrary variable J. We would like to say that this variable has been stifled by the assignment to the other variables, in the sense that no matter how you assign this variable, given that the other variables have been assigned in this way, the output of G gets determined. Okay. So this was, so that's why this is called stifling. And examples of stifling would be, stifling gadgets would be this indexing with 3 bits. You can easily see that this is a stifling gadget. And there are many other things like majority, inner product, and so on. Any random gadget is stifling. So I don't have time, as I understand that. So let me just skip all this and tell you where our new work is. So yeah, the main work that we have to, I mean, the query nodes, for query nodes, we already, in the previous work, we could already simulate query nodes using stifling gadget. But the main work here is, as I said, in forget nodes. When you have a forget node, somehow you are maintaining a representation of your affine space so far. Yeah. And now you have to go from the affine space so this was a constrained representation. So any affine space is given by a set of linear constraints, and this was the matrix of linear constraints, so which was being maintained. There was some bookkeeping going on. You were doing it in a nice way. And now suddenly you have to descend into a new affine space. And now you have to and that affine space contains you. So how do you do that? Yeah, how do you do that in a gradual way so that the invariance that you were maintaining continues to be maintained? And this turns out to be the main work. And let me just point out a very useful lemma from linear algebra that turns out to be it's surprisingly simple, but turns out to be very effective for us. To mention that, let me define a new operation on matrices. So imagine I've been given a matrix M. It's a q-dimensional matrix, so it's representing some q linear constraints that I have. Okay, and T is a vector which is selecting a characteristic vector of the rows of my matrix. It's not the all zero vector. This operation delete M comma T comma I, it does the following. It adds this row Mi to all other rows on which are included in T. It will just do this primitive row operation, and then it will just delete the row Mi. So this new matrix that you will get has one less row, which is what you would expect to get to be able to represent the affine space when you descend. Okay, so so here is the effective lemma, which is what we are going to use. Is that if I am given an affine space which is represented by this linear constraint matrix, yeah, and the affine space has one dimension more, then there always exists a vector, a subset of rows, yeah, which is not empty, such that if I do this delete operation in the way that I mentioned, yeah, this delete operation will always give me a valid representation of the new affine space. So if I started with this matrix in row reduced echelon form, then I would continue to get this row reduced echelon form. Okay, by this operation, and using this in several ways, we could maintain the invariant, a set of invariants that needs to be maintained for doing our simulation, and this is what makes the simulation theorem. This is what drives the simulation theorem. This particular lemma is actually, I'm sure all of you can prove it once I tell you that this is the lemma. It has got a very simple proof, but it turns out, as I said, very useful. Maybe there are other users of it. So since I'm running out of time, let me just skip. And come to the conclusion. So the conclusion is that we have this new depth to size lifting theorem which preserves width. This is the fact that we are able to preserve the width is important. It's therefore able to lift Rasborov supercritical trade-off for tree-like resolution to tree-like Reslin. Very recently, and we will hear in the next talk by one of these authors, Efremenko and Itzikson, they were able to give an alternative proof using different notions, and their lemma is their theorem is slightly stronger than ours because it's able to work for a larger class of gadgets. I did not have even time to talk about the kind of gadgets that we used, but they are able to use just stifling gadgets to prove the same result that we have. And thank you.